like to call upon the third speaker for our session, Dr. Hamad Umair. Dr. Hamad Umair is an assistant professor at Kamsat's University, Islamabad, where he leads a group of more than 35 researchers. He has received his PhD from the Department of Bioengineering at Imperial College London, where he was a Commonwealth Scholar.
Thanks very much for the kind introduction. The topics what I'm going to present today are the research works of my PhD students, which we performed over the past couple of years. Firstly, I'll talk briefly about the MRI, how it works, and how it relates to research, and why we are trying to reduce the scan time and what's its significance. And then I'll talk about the different methods we are using to improve the performance of MRI. And then at the end, I'll talk about the magnetic resonance fingerprinting, which is the future of MRI, perhaps. MRI is a safe and painless diagnostic imaging modality, and most of you will know that it's non-ionizing, non-invasive mostly, and it's used to detect different diseased conditions. MR hardware is composed of the magnets, the RF receiver coils, transmitter coils, gradient coils. So it's a very complicated system. I say it's the climax of engineering in terms of medical imaging. How it works is we apply the RF pulses, which are absorbed by the tissues. And then when that energy comes out, after a certain time, the signals are received by the receiver coils, and then A to D sampling is performed, and the data is stored in the Fourier domain, and then inverse Fourier transform is taken to acquire the image. So essentially, in MRI, the data is acquired in the Fourier space, which is known as the K space, and we have to perform inverse Fourier transform to acquire the image. I mean, the localization of the signals is very important in MRI because you need to repeatedly apply these three different gradient fields labeled as GZ, GX, GY in this diagram. And then the RF pulse originates, which takes the signal to a particular space in the location in the K space, and then the A to D sampling is applied, and we get one line of K space. The process needs to be repeated again, and then we apply a different phase encode gradient, and then the second line is acquired. So we need to apply a series of RF pulses, and as a result of that, the whole of the K space needs to be filled. So that's why it's very time consuming, because every time you're applying the RF pulse, and then you're waiting for the signal to come back, and then you're applying it to desampling, and then encoding it in a proper fashion, and then you apply inverse Fourier transform, and you get the MR image. So it's very time consuming. So the two main factors which define the time of MRI scan is the pulse repetition time, how long you want to wait before the signal is acquired, and also how many lines you want to acquire. So I mean, what we do is, as this slide shows, that we acquired the data in the Fourier space, and then we have to apply Fourier transform to get to the image space. Although we can play back and forth, we can always go from the Fourier space to the image space, and then from the image space back to the Fourier space. And different types of sampling techniques, as is shown at the bottom, give different types of artifacts. So if the undersampling is very regular, then the type of artifacts are different. If it's random, the artifacts we see are different. If we fulfill Nyquist criteria, then we don't see any artifacts. So it's very relative to the fact how many number of samples we are acquiring with pattern. So very recently, people have started acquiring the non-Cartesian acquisitions because they reduce the time. Previously, it was difficult to get along the non-Cartesian trajectories because our gradient hardware was not very perfect. So it had some inaccuracies in it, but now with the passage of time, electronics has improved, and we are able to better utilize the non-Cartesian trajectories, which include radial, spiral, rosette, propeller, and many more as well. Major limitations of MRI are it becomes too expensive because we are spending too much time for a patient to lie in the scanner. Obviously, it costs a lot of time and a lot of money. So that's where the parallel MRI came into existence. That somewhere around 1999, Klaus Prussmann from ETH Zurich, he proposed an idea that why don't you use multiple receiver coils to acquire data, and then that leaves us with a better chance to reconstruct images with less number of acquired samples. So that will help us to reduce the scan time. As you could see in this slide, that there are 4 receiver coils shown there, which are used to acquire images. But to perform reconstruction in this case, we should know the sensitivity profiles of the receiver coils which are there to acquire the signals. And then, at the end of the day, we get a coil combined image. So the performance we can achieve with parallel MRI is we could acquire less number of samples, and still we can have fully sampled images at the end. So if we leave, the dotted line represent the sample points which have not been acquired, and as a result we get the earliest image. There are some artifacts which are apparent in it. So somehow, if we could get a full K-space, which is satisfying the Nyquist criteria, we'll be able to get a full image. So ultimately, what we want to do is we want to start from that undersampled data, and we want to end up with at the image space. Or the other path is we start from the undersampled data, fill the K-space first in the Fourier space, and then acquire the image. So one is known as the image-based reconstruction, and other is known as the K-space-based reconstruction. So upon the scanners, the reconstruction methods exist, which work on both the ideas. So I'll explain briefly both of those. So a parallel MRI is, Cartesian, non-Cartesian, and then image-based, K-space based, and then many methods exist. So what I'm going to show here briefly is about the SENS, which is an image-based method, GRAPPA, the K-space based method, and the non-Cartesian GRAPPA, which is also a K-space based method. So firstly, about the GRAPPA reconstruction. So this GRAPPA method was proposed by Professor Mark Griswold at Case Western University, USA, somewhere around 2001. So what does it do is, if you look at the top, there are multiple receiver coils, C1, C2, Cn, and if you look carefully, the central part of the K-space has been acquired fully. And we perform undersampling towards the outer sides of the K-space. And then what we do is from the ACS, we define a matrix which is known as the ACS lines, auto-calibration signals, which are the fully acquired signals. From there, we calculate the weight sets, which can be used to fit the missing lines of the K-space. And then we apply those weights in the synthesis phase, and as a result, we get the fully sampled images. And then we apply inverse Fourier transform, and we get the fully sampled images of all the individual receiver coils. And at the end, we perform sum of square reconstruction to get a composite image. So this is the GRAPPA reconstruction process. So, one very important thing in the GRAPPA reconstruction is the correct estimation of the weights, because those weight sets you're going to use to fit in to estimate the missing points in the K-space. For that, we define the kernels, and then the kernel size could be different. It could be 3 by 2 or 5 by 4. But for the calibration purposes, the blue dots represent the points which are the source points, and the red dot shows the target point. And we know both of them. We know the source point and the target point. So we could find out the weights which can fit the blue points onto the red point. So once you find those weights could be applied anywhere for that particular part of the K-space. And if the kernel size is bigger, then it could be a similar fashion. But obviously, we'll have to calculate more number of weights. So bigger the size of the kernel, more number of weights we need to calculate. So computationally, the problem becomes more computationally expensive. So, I mean, this is what shows that we have to repeat the process. So, it's an iterative sequential process which needs to be applied again and again until we get all the different weight sets. And we fill the whole of the weight space, which we'll use later to find the missing points. So once we have that collection of the weights estimated, now the next stage comes that we want to apply those weights to fill in the missing points in the K-space. And that process is repeated again and again until we fill the whole of the K-space. And then at the end of the day, we can take the inverse Fourier transform, which will provide us the MR image. So this is what the GRAPPA method is. So what are the major challenges? Because we wanted to use GRAPPA and parallel MRI to reduce the scan time. But what happens if the practical gains in performance of parallel imaging are offset by the long image reconstruction time? And it takes a long time for us to reconstruct the image. So the key issues in GRAPPA are there are multiple sequential GRAPPA kernels which need to be repeated. And then obviously, the estimation of weight sets is a sequential process as well, for which we need to solve a system of linear equations. And then, I mean, there are multiple kernel fittings, which is again a sequential process. So there are so many sequential processes involved in GRAPPA. So what we did was, what we wanted to do in our research is we wanted to develop a method which would be parameterizable, which could do parallel fittings of GRAPPA kernels on the ACS lines, which could do parallel estimations, and then which could perform parallel interpolations in the undersampled K-space data of the receiver coils. So for that purpose, what we did is we parallelized all those. We used GRAPPA kernels. We used the CUDA kernels to do all those sequential operations in a parallel fashion, which will ultimately reduce significantly the image reconstruction time. And then we'll have the individually reconstructed multiple receiver coils, and at the end we perform sum of square reconstruction to get a composite image. So we designed 6 different kernels. I won't go into the details, but those kernels, they helped us a lot in the parallel computation, and we were able to reduce this time. So we compared our results for both the CPU and the GPU, and then we did the experiments on human head data set acquired at St. Mary's Hospital, London. So if you, I mean, if we see in this slide that what we could do is we performed the calculations separately. We could get 9x time speed up with the GPU and with the design of this parallel power in the calibration phase, and up till 10x acceleration, 10 times speed up in the synthesis phase. Overall, we could get a 9x speed up for a 2x3 kernel. When the kernel size becomes more, then we get up to 15x speed up. So it means the speed up we get, bigger the size of the kernel, better the speed up we get, because then there are more and more parallel implementations which can be done, and obviously that helps to speed up the process. So the results, they show perfectly same SNR. There is no compromise whatsoever upon the reconstructed images. So in conclusion for this part, the proposed framework is scalable to different GRAPPA parameter settings, significantly reduces the latency of the calibration and the synthesis phases. Proposed method is a suitable choice to accelerate the GRAPPA reconstruction process, as the thread creation and memory transfer overheads are negligible as compared to the speed up gains. And the future work is we want to test it more on the cardiac MRI, because timing is very important, and the data needs to be acquired much quicker in the cardiac MRI. The second method I want to explain here is the sense reconstruction, that is the image-based method. It runs off the MR scanners of many manufacturers by different names. Some people name it as M-Sense, GE names it as ESET, Philips names it as Sense, Hitachi names it as Rapid. So I mean, it's quite commonly used protocol. But again, the reconstruction times are obviously they can be offset in case if the reconstruction time is greater. So in case of sense reconstruction, what we do is we acquire undersampled data. So as a result, if there are 4 receiver coils, we have 4 undersampled data sets. We apply inverse Fourier transform on each of them. As a result, we have 4 aliased images. And then we put that data, those 4 earliest images in this particular instance, into the sense algorithm. And sense algorithm performs reconstruction with the knowledge of the receiver coil sensitivity profiles, and as a result, we get the reconstructed image. So if we look in further detail, so I1 shows if there are 4 receiver coils, there'll be 4 earliest images, 1 earliest image for each receiver coil, where the signals have been overlapped because Nyquist criteria has not been fulfilled. At the same time, we also know the receiver coil sensitivities of all the 4 coils. So we know the sensitivity of each point. For example, C11 and C12, these are the sensitivities as 2 points, and and row 1 and row 2 are the final solution image we want to have. So effectively, because of undersampling, we are getting I1, and we want to get a true estimate, which is row 1 and row 2. So I1 is actually mathematically C11 multiplied by row 11 plus C12 multiplied by row 12. So that signal has been overlapped because from 2 different locations because of undersampling. And since we have 4 receiver coils, so we have 4 alias signals for the same location labeled as I1, I2, I3, and I4. So ultimately, we have 2 unknowns, and we have 4 equations. So we could solve it easily because it's an overdetermined system. So that's what exactly we do in sense reconstruction. Is we have, if I want to write it in matrix form, I could say I equals C times rho. Rho is what we want to estimate, and we know the encoding matrix, which is composed of mainly the receiver coil sensitivities and also incorporates the Fourier encoding as well, times the alias signals I. So we could simply take the inverse of the encoding matrix multiplied by the alias signals, and we get the estimate, a true estimate of the signals. So this inversion is challenging in sense, because normally the rectangular, the encoding matrix is a rectangular matrix. And taking the inverse of rectangular matrix is, always challenging. So what are the major challenges in sense is inversion of the rectangular matrix, as I said earlier, is a complicated task. So we wanted to develop a fast method. Sorry. And a stable algorithm is required, which could perform the reconstruction process very quickly. And again, the method should be parameterizable. It should be parallel matrix inversions, and there are different methods available. We chose for the QR decomposition method. So this is this is the proposed architecture, which performs the parallel computations using QR decomposition, and as a result of that, we were able to perform those tasks of matrix inversions and the encoding matrix inversions, which otherwise was a sequential process. We were able to do that in a parallel fashion, and then that helped us to reduce the reconstruction time significantly. This is the right side shows the GPU processing platform, which we proposed, and the left side is the conventional processing. So you could see that although the GPU processing has multiple steps, because the data needs to be transferred to the GPU and then it has to come back, but still it provided us significantly better results, as I'll show in the results section. So the proposed architecture is utilizing the parallel computation of the processes by launching multiple threads. So we tested the proposed architecture on different data sets, and then the reconstruction results were perfectly the same for both. So for all the results, this is the cardiac data set, and still the results were perfectly good. So if you look at the computation times, for the phantom data set of size 256 by 256, the computation time for GPU was 7.2 milliseconds. But if the acceleration factor, which means that if more number of the k-space lines has been skipped, so obviously then more computations are required, and that increases the GPU time significantly. So it means how much time it takes. It depends upon the acceleration factor and also upon how many number of receiver coils are there, which ultimately define the matrix, the encoding matrix, which needs to be inverted. So this provides a comparison that the gray color bars, they show the GPU computation, that you could see that the proposed architecture has significantly reduced the reconstruction time using sense. So in conclusion, the QR decomposition is proposed for the rectangular encoding matrix inversion in sense reconstruction, and the proposed method is fully parameterizable. It could be extended to any acceleration factor, any number of receiver coils. The third thing I want to show is the non-Cartesian parallel imaging. As I said that previously it was difficult to use a non-Cartesian imaging, and professor used to say that the purpose of non-Cartesian trajectories is only to produce PhDs. It's of no significance in the industry. But with the better utilization of electronics these days and better performance of electronic systems and the amplifiers, it's more and more used now. One major limitation of the non-Cartesian acquisitions is you acquire the data in radial, spiral, whatever pattern you use, which is non-Cartesian, then you have to do gridding. And now that's really kills, because gridding is a very computationally intensive process, because you have to apply inverse Fourier transform to get the image. And that cannot be performed directly on the non-Cartesian trajectories. So that gridding takes a long time, and it causes imperfections as well. So for that purpose, Nicole in 2008 proposed a method known as self-calibrated graph-operated gridding, which actually what she proposed was you map the non-Cartesian positions to the closest Cartesian points. So effectively, this method is similar to the grappa method, which I said earlier. So again, it has two phases: the calibration phase, which is self-calibration phase, and the gridding phase. So in the self-calibration phase, you compute the weights, which will be used to fit the non-Cartesian points onto the closest Cartesian locations. And the gridding is you apply those weights. So first you calculate the weights, and then you apply those weights in the synthesis phase, which is known as gridding. So I mean, effectively, the self-calibration phase and the gridding phase, I'll show in a graph after a couple of slides, that the self-calibration phase takes much less time as compared to the gridding phase. Gridding phase takes a lot of time. What we did was we wanted to accelerate the non-Cartesian parallel imaging using GPU-based SC-GROG, and again, the method should be parameterizable, and we also wanted to use lookup tables, because it's important what happens if at one Cartesian location more than one non-Cartesian points fit into, then how we are going to choose which one is the best. So we wanted to use lookup table, which was, I mean, a very unique concept. And the parallel access to the lookup tables for concurrent shifting was required as well. So again, we developed different kernels for this, and mainly 3 kernels given there. I won't go into the details, but they helped us to perform both the synthesis and the gridding process in parallel. So we tested the method on the radial data sets, cardiac data set and human head data set, having 30 receiver coils and 12 receiver coils. This slide shows that most of the time is taken by the gridding process, which is shown by the brown color. The blue one shows the self-calibration. You could see it's only about 8% or so time which is using the calibration process. So mostly time-intensive process is the gridding. So what we did was we performed the experiments on the Shep-Lugan phantom and for different number of projections. And then we could see that for the gridding, we were able to get up to 12x, sometimes the 20x, 30x with 400 projections. Significant acceleration was achieved. If you look at it's the overall computation time, so that the previous slide was only the gridding time, and for the overall computation time, it goes up to 7 times better as compared to the conventional CPU processing. If you look at the images, they look perfectly similar. There is no difference, same RMSE values, so it means that the proposed architecture does not compromise any of the reconstruction processing at all. So even these line profiles, they show that both the images are perfectly overlapping. Yeah, so the speed up achieved is good. So that's for the second data set, that up to 20x speed up in the grading process, and up to 7x speed up in the overall process, including both the phases, for the 12-channel human head data set. And you could see the results are exactly the same. So even for the 30 receiver coil data set as well, so significant improvement is achieved in terms of reconstruction. So to conclude this part, proposed framework is scalable to different grading parameters and can be used with many non-Cartesian trajectories. It employs lookup table to avoid the race conditions. It can be used to accelerate the gridding process significantly. It reduces the overall computation time. The last part of my presentation is the magnetic resonance fingerprinting, which was a very recent work proposed by Dan Ma at Case Western Reserve University, USA, and the paper was published in Nature in, I think, 2015 or so. So I know that Siemens is working on magnetic resonance fingerprinting, and it said that they are going to put it on the scanner by 2020. So we worked in close collaboration with the inventors of magnetic resonance fingerprinting, and they are our co-authors in a couple of papers as well. How does it work is, one major limitation of current MRI is we always say that it compares the relative signals. So for example, at 1.5 Tesla scanner, this image will look different. At 3 Tesla scanner, the image will look different because it's measuring the relative values of the signals. So what MRF does is it actually helps us to measure the absolute values of the signals, the real-time values. So the concept is very similar to the fingerprinting process we use normally. So it does the randomized acquisition, it involves pattern recognition, and then it extracts information. So it's just like the fingerprinting process. When you take your fingerprint, it's compared with the database of the fingerprints available. It does pattern matching, and for wherever they get the match, you get the whole information about it. So the same thing in MRF, magnetic resonance fingerprinting, what it aims to do is it wants to build up a fingerprint for every type of tissue. So when you apply the RF pulse, the signal is absorbed by the tissue, and then it comes out. As soon as the signal comes out, it will be matched to a whole dictionary of the signals, which has been made by using block equations. And then, by the match, it will find out which is the best match, and that will give us the signal. So that is actually revolutionary because obviously it will be the absolute value of the signal, which you'll be obtaining from the already pre-calculated mathematical models, and very less effect of noise as well. It could be used in many applications, and people are really looking at a lot of applications for this. So what is the major challenge in MRF is the execution of MRF requires a considerable amount of computation time, because you have to perform pattern matching, you have to do dictionary development, which is a lot of computationally intensive process, and it takes hours and much long time conventionally. So what we wanted to do is we wanted to reduce the computation complexity of MRF algorithms. We wanted a method which would be parameterizable, and then we wanted to accelerate both the dictionary development and the pattern matching parts of the MRF algorithm. So this is the conventional fingerprinting process. You could see there are many loops. So it works in a sequential manner because you have to do all those simulations of the dictionaries by solving the block equations in a very sequential manner. And this is the pattern matching. Again, you can imagine for the pattern matching, machine learning has been there, always the hot favorite. So, again, a very sequential process. So as part of our research, what we did the loop enrolling. So we identified where we could remove the dependencies, and we could find out we could do parallelism properly, and we developed a separate architecture for the proposed parallel. This is a proposed parallel architecture for the dictionary development algorithm. So you could see it's doing all the operations in parallel. very less number of redundancy of the clock signals or repetition processes involved. And this is the parallel framework we developed for the pattern matching part. Again, it's hugely parallel, and it can launch a huge number of parallel threads, and then we could reduce the scan time, the reconstruction time significantly. So we used the NVIDIA GPUs for this, and to test our architectures, and the results were amazing. We were able to get, if you look at the bottom table, the conventional fourth generation on i7, the computation time for the process for the for MRF used to take the above two tables, they show the dictionary development and pattern matching separately. So you could see that conventionally, it was a longer time, but the GPU implementation, the parallel architecture helped us reduce the time. We were able to gain up till 18x speed up in the reconstruction time. So where it used to take 348 minutes on MATLAB, on C++, 90 minutes, we were able to do that task in 4.5 minutes. So it was a significant achievement. The results were perfectly the same. These are the synthetic images, and there's no difference images. So it means that the proposed architecture does not compromise the quality of reconstruction anyway. So to conclude this, the accelerated MR image reconstruction without any compromise on the quality of the image, MRF algorithm is accelerated without any functional modifications. So we did not use any principal component analysis or any other further advanced signal processing techniques, which if used will further reduce the time, obviously, and that's what we are going to do in future. Our future work is we are also incorporating we have started using the machine learning and artificial intelligence somehow, because there is pattern matching and we are already working on it. 2 of my PhD students are involved in it. We are grateful to NVIDIA for providing us 6 GPUs a few years back, which we used to do all this research, and that has helped us to produce 7 PhDs so far in our university. We're very grateful. We have a long list of publications. I've selected some of those, and this is a long team. The good thing about our research team is it includes the undergrad students, it includes the master's students, it includes the PhD students, and it includes the postdoctoral scholars as well. All of them work in a team, and I'm grateful to Dr. Umair Inam and Dr. Irfanullah for providing me help in this presentation. I was only the presenter. It's the work mainly done by the students. Thanks very much for your attention.